Okay, I think it's about time. It's, yeah, 6:30. Okay. I think they are ready. The recording. Cool. So let's get started. Welcome back to our software testing and quality assurance class. And what I'm going to do next is, I guess first I'll see if there is any question about anything we have covered so far, and then we can move on from there. I had some people ask me about project questions. As I promised, I will spend more time talking about project probably towards the end of the next class. Okay, because what I intend to do in this class and in the next class is to give you a kind of survey or kind of grand tour of the quality assurance, and so we'll be looking at the different quality assurance techniques and related activities, and those will be kind of corresponding, many of the things will be corresponding to the part 3 of our textbook. So we will not go into each individual chapters, but we will be looking at the main ideas behind each of the chapters. So we'll go particularly for when we do the chapter 3, which is kind of our classification of the different quality assurance activities and techniques. When we go through there, we are not just going to stop by the classification, but also looking at the ideas behind each of the individual quality assurance activities, and then we will be kind of using that as a preparation for you to start thinking about your project. Okay, so we will be discussing, spending quite a bit more time on the project next. So let me see what it is. Hello? The microphone? Oh, okay. Okay. I was told I don't really need the mic in this room, but I was told that I need to put this on now. So I'll put it on. That's okay. Yeah, I remember last time we had some problem with the battery. I went there and they said this room was very well mic'd, and so yeah. So anyway, it's good. So that's what we'll be doing in this and the next class. Okay. So before I resume with our regular class material, I want to alert you to one of the small change in our class webpage here. Okay, let me switch over to the presentation PC here. Okay, so the small change is here in the office hours. Okay, remember that I told you that I might need to tweak the office hours a little bit. Okay, it turned out that Wednesdays. Oh, I think this one was not the new version. Okay, yeah, this is the new version. Okay, so the office hours is Wednesdays will be good except the first week of each month where I have meetings in the afternoon. So we will keep Wednesdays except the first week of the month that I will keep Mondays, and Wednesdays is 3 to 6. And most of the Mondays, Wednesday afternoons are good for you to, if you have questions to ask me, but officially, because we are supposed to list 3 hours of official office hours, so I'll put a Wednesday normally, and then the first week of each month, it will be a Monday. Okay, so that's a small change to the office hours. Homeworks, I haven't posted anything yet because I'll be kind of waiting until the end of today's class, and I'll be posting homework number 1 in a couple of days. So maybe I'll make some small change depends on how much material we cover towards the end of today's class. So just watch out for the homework posting. Okay. Again, there's there's some questions about Blackboard. We haven't posted anything on the Blackboard yet, okay? Because most of the class material is really on the class webpage, okay? So later on, when I start posting the homework assignment and other things, I'll be using the Blackboard, and so by the time we should have the merged Blackboard, so everyone will be using the 7314.701C section. So for the on-campus student, you are automatically in that section. So for the distance student and for the undergraduate student, okay, you will be merged, and so you will be looking for that 7314.701C instead of whatever your official section is. Could be 5314, some of the 701C, or 7314, 498, 418, or whatever kind of section numbers you have. We will, in Blackboard, we will only use the 7314, 701C, okay? Yeah, so all students should be using this one, okay? Okay, so any other questions? No? Okay, so let me move on to our slides. Okay, so in the last week, just before the end of the class, we were talking about the quality and the quality expectations, and so we kind of touched upon those things already about quality expectations from the customers, user, and so and also we looked at their quality perspectives from Barbara Kitchingham and Sharon Lawrence Fleischer. Okay, so we will be kind of focusing on the two of the main expectations from the two perspectives. One is the internal producer's perspective, one is external customers, users' perspective. Okay, and so we kind of talked about that. Okay, and what we want to kind of discuss a little bit next is about some of the framework that's commonly used outside there in the industry, and also actually people took their effort to come up with some standard that in our book we covered 9126, ISO 9126 standard, and there's actually a successor to that standard. Okay, but it's essentially the same thing. So to be consistent with our book, we still use 9126. Okay, so in 9126, ISO 9126, essentially what they did there is that they looked at the quality from not really from the different perspectives of who's looking at the quality, but looking at the quality. Quality contains this, contains that, contains what. So what are the characteristics or attributes of quality? Okay, what are the elements of quality? Okay, so they are looking at more of the kind of structural construction, constructive kind of way of quality instead of look at who's quality to who and from what perspective. So they later on we will be calling those things quality attributes, but in the ISO terminology, they call it quality characteristics. Okay, so in the ISO 9126, they essentially used quality characteristics. They have a hierarchy of characteristics. Okay, so on the top level, they had 6 characteristics of quality. So those are the functionality, reliability, usability, efficiency, maintainability, and the portability. Okay, and actually, if you look at it closely, some of them are kind of related to each other. Okay, so for example, maintainability and the portability, they are kind of very closely related to each other. If it's something is maintainable, they are probably more likely to be portable. Okay, if they are likely to be portable, they are more likely to be maintainable as well. So those two are kind of very closely related. But you look at the other things, they are probably not that closely related. They each cover some specific areas. For example, when you look at the functionality, we mentioned this is something that every software product, everyone looking at it, should care about. Okay, what is this software doing? Okay, what's the function of this software? What is needed and what is this is providing? Okay, so from the customer perspective, it's I need this. Is it there? From the developer's perspective, the customers need this. Do I provide those? Okay, so look at the need and meeting the need. So do I have this provided in my software? Okay. In some other kind of literature or in other companies, sometimes this is also called a capability, functionality, capability. You are capable of doing something. Okay. Are you capable of doing something or not capable of doing something? So functionality is sometimes used interchangeably with the capability. Reliability is something that, okay, you said it's there, but is it really doing it correctly without causing a problem? Okay, you said that you can do addition. Are you really doing addition correctly or not? Okay, so you claim that you can do addition. I can do addition, but I added 2 and 2. I get a result of 5. Okay, I'm still doing addition. It's my strange way of doing addition. Okay, but that one, then you get the wrong result. Wrong result is incorrect, and that is what we call a reliability problem. Okay, so a reliability problem is that essentially you have something wrong, when you do those things. This something wrong can be catastrophic, can be minor. Okay, so for example, that you can crash. I entered a 2 plus 2, your system crashed. That's a very bad problem. Okay, I entered 2 plus 2, you got 5 back. That's probably not such a bad problem. It's still a pretty bad problem. I entered 2 plus 2, you give me 4.0000000, 17 zeros and then 1. Okay, so that's a precision problem. Okay, and so maybe you are doing, instead of integer addition, you are doing some floating point, and there's some thing somewhere in the round off or something that you have some precision problem. Okay, so in that case, I got 4.17 zeros and then 1. That is not as big a problem, but it still is a problem. Okay, it's still a minor problem. So in software engineering, in software testing, in quality assurance, we call all those things the wrong result failures. Okay, we all formally define those things. There's something wrong. Okay, and then we will look at the failures, we look at faults, and we look at the errors. Okay, and then usability problem is something like is this easy to use, effort to use, and is it easy to use? For example, that I looking at use this simple example doing addition again. Okay, do I have a keypad input for the 2 plus 2? Well, if yes, that's probably okay. That's easy to do. And maybe sometimes that while you're doing integer additions and you don't have that input, you have to manipulate and drag one token, drag another token, that's 2, and then you drag another 2 tokens, 2 groups, and say add. You can do that, right? That's still addition, integer addition. You have 2 things in one bucket and another 2 things in another bucket, and then you will press something to add. You can do that, but that is probably not a very efficient way, not a very usable way for people to do it. It's not easy for people to use. Okay, but similarly, when you're doing some symbolic manipulations, you can say, oh, all the symbols I can map them into numbers. I use some encoding scheme. Okay, so whenever I see red, it's a 01001. It's red. Okay, whenever I see a green, it's 0000111 or something like that. Okay, and you can do that, but then it's very hard for people to learn that you have that encoding scheme, and it will be probably hard to use. Okay, so in that case, it's not a functionality problem, it's not a reliability problem, but it is a usability problem. Okay, it's very hard to use. Okay, so usability, efficiency, looking at the resources that you're using. Okay, are you using your resources efficiently or not? Okay, for example, that when I was back in IBM, when I was doing some of the reliability analysis and modeling for IBM, we got a tool from NSWC, Naval Surface Warfare Center in Dahlgren, Virginia. I got the source code for the reliability modeling tool. In that modeling tool, that they need to convert every data sequence into an array of 1001 entries. Okay, and most of the times I don't have that many data points. Most of the times I have 30 data points or 50 data points, but I still have to add all the zeros to that and use up the storage space for those fixed array. Okay, so in that case, that program design. Okay, I'm not criticizing the tool because that's really an old tool and a quite a useful tool. The program design was not very efficient. They didn't really make efficient usage of the system resources. So they have fixed arrays for what are kind of a flexible array would do, and save a lot of space. Okay, so efficiency is another concern. Maintainability, can you really make it easy for people to perform those maintenance tasks? Okay, So, for example, that is sometimes you need to make some corrections, you need to improve something, and you need to adapt to a new environment. Is it easy to do those kind of maintenance activities? Okay, and the probability if you port from one environment to another environment is easy to do. So if it's easy to do, it's a system providing some support for you to do those things. We say it's good in reliability, good in functionality, good in usability, good in those kind of things. If not, we say they're not too good. And under the ISO 9126, they have also some sub-characteristics. So they have a kind of a tree structure. So they have the characteristics, top level 6 characteristics, and then they have the next level some sub-characteristics. Okay, so that's the ISO 9126. Okay, it has been the kind of more influential among the frameworks or mega frameworks about software quality. So it influenced lots of other people's conception about quality. Okay, and but there are some limitations. For example, that a strict hierarchy may be somewhat questionable, and also sometimes when you look at when you have this rigid structure, sometimes you have those different concepts that are interconnected. Maybe it's a little bit harder to express that. Okay, so. But it's a really nice comprehensive framework, so lots of other people and other companies adopted that, and some people made some modifications to that. So we can look at a few of the modifications to those things. For example, that adaptation of ISO 9126 has been very common in industry. So different companies, they have their own definition and interpretation of quality, and most of them are some kind of rehash, further improvement and refinement, or kind of select a subset of the ISO 9126. Okay, so one typical example of that is the IBM's definition of quality, that they consist of those different elements that's kind of similar to the 6 top quality characteristics in the ISO 9126. For example, IBM said their quality definition is the COPRIM DSO: capability, usability, performance, reliability, installation, maintainability, documentation, service, and overall. Those are the COPRIM DSO. Okay, so I was in IBM, so I was in the quality, so we had to look at all those things, and so that's kind of something that we look at each project. Okay, so when you look at this, it's kind of similar to the 6 attributes. Capability is the functionality, usability is there, reliability is there, performance, it's kind of something related to the efficiency aspect. So, but it's the external aspect of the efficiency. Okay, and various other things, the installation, portability, those kind of things are related. Okay. And there are also sometimes when people look at quality at the different application domains, but not just looking at one company at a time, is that people say, okay, there are certain things are more important in this domain than in other domains. Okay, so for example, for the web application domains, people said, okay, there was a paper talking about this, and people generally agree on this thing. It's for the web application domain, there are 3 key quality attributes. Okay, that's the reliability, usability, and the security. Okay, when you look at this, okay, you say, oh, there are certain reasons for those. Okay, reliability, actually, they oftentimes people roll the capability and the reliability together. Can you do it? Can you do it correctly? And they roll it together. If you can't do it, it's kind of like you cannot do it correctly. Okay, so that's sometimes people roll it together, because if you can't do it, they say you have 0 reliability in that particular aspect. Okay, so that's why sometimes the functionality and the reliability often roll together. So they say reliability, you must be able to do those things for me correctly. Okay, another thing is that because for the web environment, you generally target the mass market. Anyone who got a computer is supposed to be able to access and use this thing. So usability is very, very important. And security, because you are in a shared environment. When you are in a shared environment, there are lots of things that can happen. Okay, if you have a monolithic, dedicated environment, then you don't really care about the security as much. So if you have your dedicated things in the lockdown room, and then things that as long as you make the facility secure, you don't have to worry about software security, hardware security, and communication security, and all those other securities. Okay, but now we are in this wired world, in the interconnected world. Then security is a major concern. Okay, so for the web domain, similarly, if you're looking at it for the internet, for the cloud computing, this security is a big issue. Okay, so you not only want to make sure that it works under the normal situations, but it's secure. It can have some degree of assurance against some kind of malicious attempt. Okay, so people look at this for different domains. You have those different things, and there are other quality frameworks and mega models that are people were talking about quality, and Macau has a framework about the factors, criteria, and the metrics. Okay, so kind of it's a little bit more of a operational view. Okay, so you look at the different factors. So it's kind of like attributes, and then you look at the criteria that may involve some of the people's views and perspectives, and then you will connect them together through some kind of quality metrics. Okay, and Vic Basili had came up with this so-called GQM paradigm, goals, questions, and metrics. Okay, so essentially you are looking at a goal-oriented approach instead of a general one quality definition fits all. Okay, he's more looking at when you do some measurement to quantifying things. What are you trying to quantify first? You try to look at the goal first. Then you look at if you want to quantify that, what are the specific questions? Okay, if you want to try to achieve that goal, what are the specific questions that you can ask? When you ask those questions, that can kind of refine your goal a little bit, and also consider your environment, your stakeholders, your participants. Okay, and then you can quantify the things with your metrics. Okay, so that's a GQM approach. That when you look at the quality, you can use which quality are you talking about? What do you mean by quality? Okay, from whose perspective? So what kind of things are you trying to do? So I say I want to improve the customer satisfaction. Well, that is your goal. And then your customer satisfaction, what are the elements to your customer satisfaction? To improve the customer satisfaction, what are the things that your customer cares about? Okay, and then you look at those questions, and then you come up with some metrics. For example, that say, for example, my customer in this case is a scientific computation community. That they using supercomputers, doing the simulation about the Big Bang, about the beginning of the universe, or things like that. So for them, performance is very, very important. But the usability is probably not that important because they are specialists. Okay, they can deal with some of the things. Okay, so the performance is very important. And then you look at the things. Usability is not as important. Okay, performance is important, and then you look at some of the kind of performance. Then you refine it to the performance in terms of the usage of the resources, and then is the time more important or space more important? Okay, or some of the other things, and then looking at what's the specific measures that can support this customer satisfaction. But when you have customers for some other different things, some kind of online games, okay, For online games, then you probably have a completely different set of quality attributes and the quality metrics. Okay. And then there are also other important frameworks. Then one of the very influential ones is the SEI CMM and the CMMI. The SEI is the Software Engineering Institute, okay, which was founded by Department of Defense, and it's resides in the Carnegie Mellon University. Okay, and they came up with the CMM as a capability maturity model. Okay, and then they had a newer version of that is a CMMI with the integration in it. Okay, so what they focus is that say if you want to have controlled software development with high quality, on schedule, and under cost, in budget kind of project. Okay, so successful software project, then they claim that the most important thing is the process. Okay, if you have a good process, you'll have a much better assurance that you will have a successful project. Okay, then quality is an important part of that success factor. Of course, the schedule, budget, and quality. That's typically people say, okay, those three things give me 2. Okay, it's hard to get all 3, but you can typically get a 2 out of the 3. Okay, so it's a cost. I don't care about the cost. I care about how good it is. Okay, I care about the schedule and the time. So that then I can probably spend lots of money get it. But then in other cases that there are other concerns that you say, okay, I'll get it to you quickly, okay, and but maybe it will not be of highest quality. Okay, so there are considerations there, but basically what SEI was saying is that, well, if you want to have a successful project, then process improvement is important. Okay, so you need to fix your process, and so they basically evaluate the process maturity and divide that into the 5 levels, from the complete chaotic ones to the optimized ones. Okay, so level 1, 2, 3, 4, 5, the 5 levels. Okay, sometimes people say, oh, that's a level 1 should really be level 0. You're not doing really anything. Okay, but that's their scheme of level 1 through 5. Okay, we will be talking about process improvement a little bit in terms of, because in the SEI CMM focus, they focus on defect prevention in terms of the quality focus. Okay, so they focus much more on defect prevention than other things. So we will talk a little bit more about their CMM work in connection with this. Okay, there are a couple of other things that we are not going to go into detail, but essentially what we can say is that there are kind of a lot of different definitions, different attributes, and different views around there. But there is one thing that's kind of common that everyone kind of, particularly the people from their industry, agrees that generally quality means no bugs, okay, no defects, or low number of defects, okay. And you say, in a sense, that's kind of shifting the answer to a question by give another thing that it need to be answered. Okay, so for example, you said defect, high quality equal to low defect or no defect. Then what do you mean by defect? You have to define defect. But then the thing is that when you define defect, it's probably a little bit more tangible than just quality in abstract. Okay, you can say, okay, I can talk about defects, I can talk about something that I can observe. So intuitive notion is that if you have a defect, there's something wrong. Okay, something not quite right. Okay, that's a defect. Okay, and we will refine that a little bit later. Okay, and so it's a kind of intuitive notion that's very closely tied to the correctiveness aspect of quality. Okay, so you essentially you look at the high quality means low defect, and then you look at the quality problem. How big is the problem is basically look at how big the impact of your defect is. Okay, how big the problem is. Okay, and so it's kind of most widely accepted, particularly by people in the industry. Okay, so when you say it's a high quality, that means that it has very few defects. Okay, but then we need to kind of better qualify. What do you mean by defect? Something wrong. What do you mean by something wrong? Something wrong in what sense? Okay, so that's when we come up with those different kind of more precise definitions of things associated with something wrong. In the standard IEEE definition, we have failures, faults, errors, and also when they are kind of collectively used together, we call them defects. Okay, so whenever we say, oh, I'm doing defect classification, I'm doing defect analysis, I'm doing defect this, then you oftentimes say, oh, you say doing the classification, are you just classifying the failures or faults or what? Or maybe all of them, okay? And you are doing some defect prevention. What do you mean by defect prevention here? And you are doing this and that defect analysis. Are you analyze which particular part, okay? So we have to kind of settle down, having a good common understanding, a little bit more precise definition and a better understanding about defects. Okay, so we use some terms in kind of specialized meanings so that will be our definitions. For example, we can look at the failures. Failures will be the external behavior deviations from your user expectation. Okay, so we talked about something before, like our addition program. I entered 2 + 2. The system crashed. That is a failure, okay? Because that's not my expected behavior of this program. My expected behavior is that I'll get a result, not a computer crash. I entered 2 + 2. I got a blank screen. That is a failure too. Okay. I entered 2 + 2. It took 17 days to get a 4 out. That's not meeting my expectation. Okay. Although I'm not considering this as a real-time system, but I have some minimal expectations. I'll take some time to do the computation, but not 17 days to do this 2 + 2. Okay. And maybe you could take 17 microseconds or 17 milliseconds or something. I don't care, but not 17 days. Okay. And I entered 2 + 2. I got 5 back. That's a failure too. I entered 2 + 2. I got a 4.000001 back. That's a failure too. So anything that deviates from my expectation is called a failure. And then I can say, okay, you call all those failures, obviously they are not exactly the same. Okay, that's fine. We can still call them failures. They just have the failures of a different severity level. Some of the failures may be more severe than others. That crash is probably the highest severity level. That the answer of 4.00017 zeros and 1, that's probably the lower severity errors. Okay, and the low severity failure there. Okay, so when you look at this, what you have here is when you look at a failure, you look at the system behavior, and when you look at system behavior, you do have some expectations about system behavior, and you can compare this one against the expectation. If the two things, the actual observed behavior and the expected behavior match, that is okay. That's not a failure. So that's a success. Okay. And if they don't match, then it is a failure. Okay. In testing, this is actually what we call the oracle problem. Try to look at what is the behavior and what is the expected behavior, and try to do a kind of a analysis and a match between the two. That's called the test oracle problem. Okay, and then you say, okay, I crashed the system. 2 plus 2 crashed the system. Well, why I crashed the system? I have to look. Okay, maybe I run into an infinite loop and used up all the system resources and then crash the system. Okay, maybe whenever 2 plus 2, I trigger some exception that's kind of doing some things about the power failures and things. Okay, that crash the system. So there's something wrong in your code, probably. Okay, that causes that failure. Sometimes it can be the failures can be caused by some external reasons. I entered 2 plus 2. At the time I entered 2 plus 2, I had a power failure. Okay, our power grid is not reliable, and I don't have backup power. The minute I entered 2 plus 2, the system crashed. That's not my reason, not an internal reason of the programmer. Okay, but that's a failure. But then I try to. That's why in testing and in quality assurance, oftentimes when we observe a problem, we want to see, is this problem reproducible or not reproducible? If it's not reproducible, then we don't really care as much. Okay, but if it's reproducible, say you cannot say that I did this 100 times. Every time I enter 2 plus 2, there's a power failure. There must be something wrong with this 2 plus 2 then. Okay, and so you cannot expect that kind of coincidence that to be happening all the time. Of course, for safety critical systems, then you say, okay, there's power failure. Power failure is still a problem. So your safety critical systems, you must have power backup and all kinds of other kind of redundancies and things built into your system. Okay, so that it will not fail. Okay, so that's a failure. But in most of the cases, it's probably something that you did wrong in the software that caused that failure. Okay, for example, that you run into an infinite loop. Okay, you use the wrong algorithm. You used some variables that had some auto incrementation there, and that one got automatically incremented by 1, and then that's why you got the result 4, and then 4 got incremented by 1, you got 5 back. Okay, and then you maybe have something with your floating point the operations. Okay, that you have some precision problem. Okay, so when you look at those, your floating point algorithms. Okay, your incrementation, run use of some incrementation of some variables. Okay, run algorithm, run into infinite loop, and those kind of things. Those things that you can identify, you can isolate in your design or in your code, right? So those things are the internal problems that will cause failures. Those internal problems are called faults. Okay, and you can think of this as we use the terminology in everyday life as well. So, for example, that you think of earthquakes. That when earthquake happens, that's failure. Okay, so you have all kinds of catastrophic kind of behavior of the Earth. Okay, that's in that case. Okay, and then you have lots of damage and things. What's the cause of it? Is underlying some pressure in some fault lines. Okay, so that's in the earthquake, they actually call it a fault. Okay, so that you say this is San Andreas fault and some other fault, and so there are some fault underneath, and so then when the pressure build up, and then when eventually that energy got released, and that is the behavior that you observe with the earthquake. Okay, and then we also say, okay, you use the wrong algorithm there. Use the wrong algorithm. So the wrong algorithm is the fault. But why did you use the wrong algorithm? Okay, and you can look at this. Okay, Because I was just trying to work on this thing, and I used someone else's code. Then someone else had an algorithm there. I just plugged it in. Well, I did it. That's the error that caused the injection of that thing, the injection of the fault into the system. That's called error. Okay. Error is the missing or incorrect human action that caused the fault to be injected into the system. Okay. That is the error. Okay. So in this case, that is the error is that I kind of used something from somewhere else for this one. That is improper use. I grabbed that one, put it here. That is the error. That's the action. Okay. But why is that? Oh, because I didn't have a good understanding of the different algorithms. Okay, so that's the kind of the source of the error. So sometimes people call it a mistake. Okay, and generally we don't really go that far, and we sometimes call it the error source. Okay, and because I was careless. Okay, so maybe I do understand all the differences, but I was careless. I didn't look closely. I just grabbed something and put it in there. Okay, so the error, because of some errors, the missing incorrect action, there are some fault committed into your system in the code, in the form of code, in the design, and in some other system elements. And those elements, when it's triggered, it will have a behavior that will deviate from the user's expectation. Okay, so that's the failure. Okay, so you have the causal relationship, causal chain from error to fault to failure. Okay, and then in general, that if we don't really distinguish between them, we lump them together. We call them defect. Okay, you have a question there?
Yeah. So the errors are human mistakes.
Yeah, the human missing incorrect actions. Yeah, so that's the standard IEEE definition. Okay. And actually, one of the things that's kind of sometimes a little bit confusing is that in different sub-communities in computer science, and actually in the systems communities, people doing systems network fault tolerance and those things, their definition of error, faults, and failures are somewhat different from ours. Okay, failures, people pretty much agree is a behavioral deviation. Faults is internal. Okay, and in the fault tolerance and systems network community, error is an intermediate step between faults and the failure. So we don't want to get into that kind of things, whether that's the correct definition or this is the correct definition. This is our definition, so we will be using. In the software engineering community, we use error to be the missing incorrect human action that caused the fault to be injected into the system, which is the underlying problem, which once triggered will cause some unexpected behavior, will be called failures. Yes?
Whatever examples we will be using for the errors, that will be same for the fault also?
The examples for
the errors, that will be same for the faults also?
No. The errors are the human actions. Okay. So, for example, I grabbed the wrong piece of thing and put it in here. That's the action of grabbing this thing, putting it here. That's the error. Once it's here, in here, that's the fault. But before it's in here, it's not the fault. Okay. Yes.
So, what's the difference between having like a design failure versus like a stupid thing about like divided by 0, but the user put it in a 0 in. Mm-hmm. But they weren't expecting it. So what's the difference between a design error? Is that considered a fault?
Well, yeah. That's still considered a fault, because if you are supposed to check the input, guard against divide by 0.
So the error is more like unexpected human behavior.
In this case, say for example, in your case is that the failure will be divide by 0, and you get the system crash or the not responding or something, and they're not getting a result. That's a failure. Okay, so you're not getting a result, and the system hang up or something. That's a failure. Okay, the fault is that design divide by zero code, the code that doing the divide by zero. Okay, and the error is that the action you put in there without checking your input.
Okay, so that's all.
Yeah,
Okay.
yeah. Okay, so that's the error, faults, and failures. And there are also sometimes people use the bugs, debug, and things. So we try not to use it as much because actually when people use bug, that kind of means defect in any general sense. But there are people were trying to kind of steer us away from that because in some sense that when you say bug, debug things is that in some sense is that as the programmers, as testers, as developers, you are invading your responsibility. It's not my problem. It's a bug that got encrypted there. I didn't do it. Okay, nobody did it. It's a bug. It's got in there. Okay, so it's in some sense it's some people take issue with that. You are not taking your professional responsibilities seriously if you are talking about bugs and things. Yeah. But people are still using that all the time. But we try to kind of stay away from it and try to use errors, faults, failures, or if we refer to them collectively without too much distinction, we call it defects. Okay. So with this definition, here is a very important picture. Okay. And I'll leave this picture here and we can take a break because we will be staring at this picture quite a bit. And we'll be studying this picture. This picture will be the basis for us to classify all the quality assurance activities and techniques. Okay, so which one are you dealing with in the causal chain between errors, faults, and failures? Okay, so let's take a break, and then we will come back. We will be looking at this and looking at the classification of the different QA alternatives. Okay, take a 10 minutes break. Just one moment and let me put this up. Yeah.
Is your slides available on the internet?
Slides? Yeah. They are in the book website. Yeah. Go to my webpage and click on the book picture.
Oh, book picture.
Yeah. And that's my book site.
Okay.
Yeah.
I think that's good.
So the errors happen during the input stage, and the failure is during the output stage.
Kind of, yeah. Errors is a commission. Yeah, you commit something to it, okay. And then you cause the injection fault in the system. So the failures are the ones that when you are in operation.
So when errors are injected in the system, we have faults, right?
Through errors, we inject faults.
Okay.
Okay, so error is false, and then it causes the expected behavior not to work. So.
Right. So the fault cause the failure when you trigger it.
Right.
And errors cause the faults, and the faults cause the failures.
You can say that as a general causal chain. Yeah. told them, but it's
Would they
their,
give access?
no, the thing is, it's their decision whether they give you access or not. I sent an email, I said you registered late, and so, but it's their decision.
So I just give it a try by sending them an email.
It's not, actually, it's not terrible, you can possibly in my other class, have an overview of the things.
Project work that I want to
A project is actually next week, we'll be talking more about the project.
they don't have to present the concept next week.
Yeah, don't worry. Yeah, especially you or in my other class. Yeah, all three of you are now in this class, and the other two are in the distance sections.
Three of us, just me and Nipuna, right? From the weekend format. And then John Sublet is in distance. I don't know who else is in distance.
I think you should.
We were just discussing.
Are you doing it?
If we have like 6 of us, we could have done the weekend format.
What are you doing in your job?
Let's see, I mean, if we can find
He said
6
he
of
was
them
doing
in the
job
next
and
connect.
doing what?
And the thing is that they cancel this. So well, I don't know when they told you guys about this cancellation. They told me at the beginning of August. And so we're supposed to teach 2 classes, so I'm teaching this one, the operating system.
I never did it.
Yeah.
Originally I was going to teach this one, so we can.
I missed that.
Yeah, that one should be more fun and more interactive.
Yeah, more like a fast paced.
Yeah, because this one is we have lots of distance students, you
So it's
don't
on
really.
I guess.
I know I'm not supposed to move around because yeah.
Yeah, I understand that.
Yeah.
Thanks for the presentation.
University registration system for courses.
Make the last
I'll take the rest of my project.
50. You do it, like I said. Yes. Well, other than work, so you can't use that. So.
Yeah. That was nothing now. Yeah, I haven't posted anything lately.
He would be testing usability. You would give him all the requirements of what it's supposed to do. And he would test the usability, say how well can you use it. Not what you use.
I can design the test cases and give them to him, and he goes and performs it and stuff. Because I want to do some design
Yeah.
kind of plan for the thing. You just know what the numbers is, what you expect from the output,
Yeah.
what values to choose.
Right. I mean, that's
Okay, let's go back to our class. Okay, and I said that this picture is important, so we'll be looking at this picture, and then I still have a couple of other slides in this chapter I want to finish, so we'll be looking at this picture briefly, but we'll come back. Okay, so let me continue with this. Okay, so this picture is basically depicts their general relationship among the different concepts that we talked about, the software faults, failures, and errors. Okay, so what you have here is that in the middle we have the, say for example, this in this box we have your software system. Okay, your software system which contains various faults. Okay, so you have some wrong algorithms here, some wrong variables, and some this and that wrong in your software there. Okay, and so that's the fault. That's a kind of easy to visualize. Okay, and then when you use that software, when you use that software, if that part of the software is used, then it's likely going to have some failure. When you have failure, what do you mean is that you will be able to observe something that's different from your expectation. So you are looking at, you have some usage scenarios, and then you have some result. You also observe the whole thing, and then you look at some of the scenarios and the results. They don't really match. They say, okay, our usage scenario is that I entered 2 + 2. That's my usage scenario. I got a result. The result is a 5. So that's an unexpected result. So I say I mark this one. This kind of combination of usage scenario and the result, I mark this one as a failure. Okay. So this is a failure. Okay. And so some fault caused that failure, and sometimes several faults together cause a failure. This is particularly when you have some kind of interface or interaction between the different things. Okay, so one module is calling another module, but you have some parameter mismatch. Then you will have a failure. You say, whose fault is it? Is it the calling module or the called module? I don't know, maybe both. Okay, somehow you didn't get to some agreement. Okay, if the calling module is sticking to some standard and the called module didn't stick to the standard, then you can say that's the module that's being called is where the fault is. But sometimes you don't have that clear cut distinction between whose fault it is. Okay, so in that case, actually, when you fix the problem, maybe you fix both ends. Okay, you say, oh, both ends had something, and now let's agree to something, a standard scheme. We all move to the standard scheme. Okay, so in that case, is that you actually you probably had two faults. Okay, and that caused that failure. So, and sometimes you may have some external problems that cause failure as well. As I mentioned, that you had a power outage that caused a failure. Well, that's not something. So we didn't depict everything, but what we want to focus on is that those faults, some faults will cause multiple failures, and sometimes several faults together will cause a failure. Okay, and if you don't fix the fault, think of this. This one caused this failure. If you don't fix it, next time it's used, another failure. Next time it's used, another failure. Next time it's used, it's another failure. So in that case, it's actually one fault can cause many, many failures. Okay, so you don't have the necessary one-to-one relationship, but you do have a general causal relationship there. Yes?
So if there is a fault that doesn't cause a failure?
There are possibilities.
How can we know that there is a fault?
Then probably when you do the inspection.
Okay.
Say, for example, you have a fault here. You did something wrong, okay? But then you did something wrong again. For example, you wrongly incremented something, but in another place you wrongly decremented it, okay? But somehow your result will be the end result of both this incrementation and the decrementation, okay? So you increased by one, and you decreased by one, and the end result is okay. Okay, but if you sample internal state, there are some places not okay. Okay, so when you do the internal testing or when you do the inspection, sometimes you could find some, and also sometimes that some of the fault, okay, will be in some place that is very rarely used, and maybe you haven't used it yet. Okay, so there that situation. There are sometimes you call it accidental or coincidental correctness because of some faults cancel each other. That's an example. Okay, and sometimes that you may have a fault. The fault is in the dead code. For example, that code no one ever used it, so it's still a fault, but it doesn't matter. It's immaterial. Okay, because it will never be triggered if it's a dead code there. You inherited something, and then you inherit something that definitely has some fault in it, and you never use that part. that part, then you have the fault or you will not have failure. Yeah. And the errors will be the missing or incorrect action, and the action will be here that caused the fault to be injected, but we want to depict also the error sources. Okay, so because of this, I had this action that, say for example, because I didn't understand the difference between this algorithm and that algorithm, I used the wrong algorithm. I select the wrong algorithm. That action is the error. But the source of that error is that my misunderstanding, okay, of the difference, or my lack of understanding of the different algorithms, okay. And so we can depict this picture here. And then with this, then what we can say is that if we say quality is something synonymous with no defect, high quality means no defect or low defect, then if you want to deal with the quality problems, you deal with defect problems. Okay, that is the quality. With this kind of view, you can say, okay, when I do the deal with the quality problem, when I assure quality, I try to do something with this defect picture. If the defect is there, I try to remove it. Before it's there, I try to prevent the injection of it. And if something I cannot remove, can I still prevent it from occurring? Okay, so I can build in some internal cross-check, for example. Instead of I always trust you to give the correct answer, I cross-check your answer with someone else's answer, and then give the consensus answer. So instead of just ask you to calculate 2 plus 2, I ask someone else to calculate 2 plus 2. And then you say, do you agree with each other? You both say 4. Okay, I say the answer is 4. If one says 4 or one says 5, I say, I don't know. Okay, so I need to go back. Okay, or sometimes I say, okay, let me ask 3 people, and then we vote. Okay, and then 2 people said 4, and then 1 said 5. Then I vote 5 out. But that's not a guarantee. But that gives you a little bit additional level of assurance. Okay, and because the thing is that generally, if you have the correct result, they tend to agree. When you have incorrect result, they tend to diverge. They tend to go all over the places because the incorrect result, there are simply more possibilities of incorrect for doing something wrong. Okay, there are more ways for doing things wrong than doing things right. Okay, so if you trust that one, and then you can say, okay, most likely if some people agree, and then it's probably the correct answer. Okay, but that's not a guarantee. Okay, and in the Middle Ages and before, and most people agree that the Earth is the center and the sun revolves around us. That doesn't make the sun revolve around us to be the truth. Okay, and when you have more agreement, you generally at least you get a little bit more assurance most of the times. Okay, so that's the basic thing, and we will be seeing in our next chapter. We basically say, what do we do with those pictures? How do we deal with those problems? Okay, and I want to summarize this part, and then we can move on. So there are many different definitions of quality. Okay, and what we do here is that we adopt this kind of a correctness-centered view of quality. Okay, so when you look at the quality, you can look at it from the different views or perspectives, and you can look at the different elements or attributes. Okay, from the views and the perspectives, we will be looking at both the customer, external, user view. We'll also be looking at the internal developer, tester, and the internal company view. Okay, and when you look at the correctness, whether it's correct or incorrect, generally If it's incorrect, from the external view, look at the behavior. That's a failure, okay, when it's incorrect. Okay, and from the internal view, something incorrect in my code, that is a fault. Okay, and then of course then you have the kind of the causal view and the process view that says this caused this one, and then that's the error. Okay, and then there are various other attributes related to quality we are not concentrating on as much. So those other attributes, for example, maintainability, readability, portability, usability, installability, and those other things, they are related to quality, but we don't focus on those things as much. Okay, but you can extend and look at the things in what is our expectation on maintainability, and if we deviate from that expectation, you can consider that as a problem, and you can similarly define maintainability related errors, faults, and failures, and things like that. Okay, so that's our summary of our views. And there's in the book there's also some kind of a historical perspective. I'm not going to go into details. Mainly we are looking at some of the things historically. When you look at the manufactured good, it's the main thing is because it's the process itself is fairly fixed, and you don't have much of the so you go through a long design process, and then you going through the manufacturing process. Okay, and the most of the problems that people deal with are they separate the design and manufacturing clearly. With software, we don't have that very clear separation. Okay, your implementation and your designs are kind of together. The actually duplication of the software is almost guaranteed to be defect-free. Okay, not 100%, but a much better guarantee of being defect-free. Okay, you copy the software, and one copy is almost invariably the same as the previous copy. Okay, because of the digital technology and things. Okay, and so we do have a different focus in their manufacturing and in software. Okay, and also people looking at the service, and then look at in the service industry what are the key things that people do. For example, instead of people check about the defects, but more about the follow-up. How do you follow up and make the customer happy? Okay, so sometimes if you make some mistake in the first place, if you address the problems, and then you can make still make a customer happy. Okay, and so sometimes people say in the service industry, you are not really looking at the defect, you look at the defection. Okay, people abandon you, going to somewhere else. Okay, as long as you handle things properly, you probably won't have defection, even if you have a defect. Okay, and there are also some expectations about the things in the traditional view and in the new views, and so in our information technology software industry, we expect some kind of combination of not only conformance to your standard, but also some adaptability, some innovation. Okay, so sometimes people often say, okay, look at the Windows. Okay, Microsoft is such a big, powerful corporation. How come they cannot do a good job and make their Windows really reliable and secure and of good quality? Then people from Microsoft say, oh, they look at the configuration and the way people using it. It's, they expect us to be to all things to all people in all kinds of environments. Okay, so there are some expectation of adaptability. With traditional products, you don't expect it to be used, abused as much. Okay, but with software, people try to use it, abuse it in any way they want, kind of. So there are some different expectations. So that's the conformance and the adaptivity, and people always expect you have something new. Okay, you have new releases, you have new things, and they always expect some innovation and things. So that kind of rolled into the expectation for quality. So there are some of those discussions there, and there's also this historical perspective on the in a paper by Musa and Everett. Okay. And they said that when you trace the history of software engineering, that we moved from the functional stage to schedule stage to cost stage to reliability stage. Okay, so they wrote the paper back in 1990, and they say the 1990s the age for reliability, because they say in the early days is really whether you can do something or not that distinguish one from another. Okay. One company from another, one product from another. So it's the capability of the product. Okay, so if you can do this, then maybe you are the only one. Okay, and then people will buy your things. Okay, so for example, a lot of things from the early days that IBM did this and that they are the only one did that. Okay, and then let's say that when you have more competition, who can get to the market faster? And then with the mass market, a lot of competition is not only you can get to the mass market faster, you also need to be very low cost. So you need to compete on the cost. Okay. So from the IBM perspective, because I was in IBM, and at the time they still had the operating systems and the PCs. Okay. So they had their version of the operating systems. For early days, they have the PC DOS, and then they had the MS DOS, okay, and then they had the MS Windows. The PC, then from the IBM, they had the OS2, okay, and at the time I was in IBM, they still had the OS2, and lots of people claim that the OS2 is actually better quality than Windows, but IBM could not compete on the cost front, okay. And so they spent lots of money on those things, and eventually they couldn't keep up with Microsoft, and so they abandoned that kind of business. You can do this better. We will focus on what we can do better. Okay. And then when you say after this, when you look at just the cost, if people really need to rely on things, then reliability is very important. So that's kind of their perspective. Okay. There are also some perspectives about history based on the measurement. Okay, so you look at quality, and can you really formally quantify some of the things, manage things? Okay, so some of those things I'm not going into detail, but the key thing takeaway there is that there are many different ways of looking at quality and quality problems. And you can look at it from the different perspectives. You can look at the different attributes or different elements of quality. But with what we will be doing in the rest of the semester, we focus on the correctness-centered aspect of. So that's the element we focus on. That's the attribute we focus on, and we focus on that from both the external customer perspective and the internal development perspective. Okay, so when we talk about the black box testing, talking about the usage-based testing, it will be more on the external focus. Okay, but still correctness focus. And when we talk about the white box testing, structural testing, we looking at more of the internal focus. Okay, and the internal perspective, but we still focus on the correctness aspect. Okay, so that's the quality here. We talk about what is the quality and some important definitions and this picture. Okay, so this picture will carry us right through to the next chapter, and which is actually the heavy chapter that we will spend at least 2-3 hours on. Okay, so because as I mentioned before, I want to use that as the anchor so we can talk about all the different important quality assurance activities and techniques. Okay, so this chapter is about the quality assurance. Okay, let me use this that actually moves better with this. So the quality assurance. So we now define the quality. Okay, and now because we say defect is so closely related to quality. If we want to assure the quality, we want to assure you have a no defect or low defect. And then with defect, we have the error, fault, failures, and say, what can we do with it? Okay, so this is our picture here. See, this one looks almost the same, except we added some defense against this causal chain. Okay, so you still have the error sources through some action, faults get committed. And those faults, when triggered, you get some failures observed. Okay, and what we're trying to do is that, as I mentioned before, we say, okay, if it is there in the system, we can test it, and we can find it out. We find out whether you have a fault here in the system or not, and we can remove it. Okay, so that's the center part of the thing. We do the so-called defect removal or fault removal. Of course, if you want to remove it, one way to remove it is to remove it with everything else. Okay, that's what people call throw the baby out with the bathwater.
The whole component.
Okay, yeah, you say get rid of the whole component, get rid of the whole thing. Okay, yeah, sometimes you do to a degree. You say this component is fairly bad in some sense. Or I have lots of problems with this component, so I get rid of this. I redo this component. Okay, so that's one way, actually, to do this. Okay, but most of the times, you don't have the money, you don't have the time, you don't have the luxury to throw away the whole thing and redo it. Okay, then in that case is that you'll find out what exactly is wrong, and just fix that part. Okay, of course, after a while, maybe it's more costly to find out what's wrong and fix it than throw it away. That is actually the theory by Belady and Lehman, and they say that through software evolution, you change, involve, and eventually you throw it away, and then you go on to the next cycle. Okay, and then the next clean slate, and you can do something. Okay, but we are mostly concerned with that something, try to fix it. Okay, so try to fix it. We talked about testing. Testing, essentially, what you do with testing is that you say here, this thing, for example, this F3, fault number 3, is going to cause this failure. Okay, when it's used, it's going to cause a failure. So when I do the testing, I still observe a failure. Okay, so my testing will be kind of similar to actual usage. But when I do the testing, I observe there's a failure. I document it, and I make sure it's reproducible. And I tell the developer, the designer, or the developer, who's responsible for this part of this function or this module or this unit. Okay, he or she will be looking at what went wrong from your execution information, and maybe go through various poking around additional execution, or maybe she's very smart. She said, okay, I know what's wrong. I fix this thing. After you fix this thing, I run it again. It's okay. Okay. Now, what effectively I did is that I observed failure, went back, fixed it, removed this, made it clean. Okay. So this thing got wiped out. Okay. So this F3 got wiped out, so it got removed. So that's the testing. So it's when going through a lengthy process of observing failures, going back and find the problem, fix the problem, retest, make sure it's gone. Okay, so that's a defect detection and removal. You're actually detecting, observing failures, and removing faults. So there's a gap there. You're detecting failures, you remove faults. So you must do something to locate the fault. Okay, and so that's a part of the responsibility. Sometimes it's a part of responsibility. Mostly the responsibility lies with the designer, developer. But sometimes the developers can help you to locate that fault and remove that fault. Okay. Then sometimes you say, okay, this is probably good for something that you commit to the code. What about the design fault? Okay, I had a wrong design. Okay, wrong design. If you wait until it's implemented, it's probably going to be implemented in various different places. Okay, and if you can catch it early, that will be much better. Okay, but how can you catch it early? You cannot really run it and observe the things. Sometimes you may have some mock-up and simulation to see if this design is implemented, what the system will look like. Okay, so you have some simulation, some kind of those facilities to help you with that. Okay, so that is actually you can test the design through simulation. Okay, but most of the times is that you say, oh, I can check, I can look, and see if there's anything wrong. Okay, so when you check, you look, and then when you finish a part of the coding, you're always supposed to be reading your code before you throw it to someone else, or even before you compile and test. Okay, so you're supposed to read your code. Okay, when we write code, we do that, and when we write other things, we're supposed to do that also. If you don't, then there are sometimes very embarrassing mistakes and things. Okay, and so for example, that sometimes I write an email or write some message to people, and especially now with the mobile device, and it's so easy to make a mistake. Okay, and then you turn on the autocorrection, and the autocorrection oftentimes make all kinds of terrible corrections. Okay, and so then you are supposed to check it before you send it out. Okay, so you don't want your users to see it. You want to see it yourself, and before you do something. And so this is similar ways. You look at the design. You look at all kinds of other things that in the process. You can do some kind of critical self-examination, or ask friends, ask colleagues to help you examine this. See, this is when you do it in a little bit more formal way, we call it inspection. Okay, so you look at the inspection, and then that the key advantage of that is that you can still find some of those problems, remove them, and you can do it anywhere. Okay, in any phase, before you have a executable, finished or partially finished product. Okay, you can do the inspection. Okay, so that's why people doing all these things all the time. And think of the things in the food industry. Okay, people do the inspection. They inspect the production line, they inspect the source, inspect the things that make sure that things are good. Okay, and the testing is the same. You have the food in the market, and people use it, and that's the field testing, and then you can say before that, and you can have some other testing, and then see if this one had the passes some kind of health standard or some other standard or not. Okay, conform to the health standard or not, and then you find the end product that this thing contains some very harmful substance. Okay, could be some germs, and there could be some chemicals and things, and you say, okay, this is no good. Okay, but before that, you can probably do some inspection. Okay, and so sometimes the inspection can be external, people doing the inspection, like the FDA, the Food and Drug Administration, they can do the inspection, or sometimes you do your own inspection and you document your inspection result. Okay. It's for your own good, because you don't want to have massive product recalls that not only you lose money for that, and you maybe damage your reputation to the degree that you can no longer be in the business. Okay. So inspection is a very, very important part of this. Okay. And then you say, okay, if it's there, I can remove it by some testing, by inspection, by some substitution, okay, by various things. So I can remove some defect from the system, okay. But you say, people say, okay, if think of the health analogy, food and health analogy. You get sick, you cure the sickness. Okay, you have bacteria, you get rid of the bacteria. You use antibiotics to get rid of the bacteria. Okay, but what if you can prevent it and you get infected in the first place? Okay, that would be much better. Okay, you have some kind of a preventive actions. Okay, so when you do the preventive actions, is that you do something upfront. Don't inject that fault into the system, or sometimes purposely inject some fault so you will be immune to the problem. Okay, so those are some of the preventive actions. Okay, so for example, that in some programs you say, oh, people are not really proficient with this programming language, and they did all kinds of things. They used the Fortran features on this Java program. Okay, and they kind of write Java programs as if they are writing Fortran code. Okay, so maybe they use some kind of things wrongly and things. Then in that case, you say, okay, if I can have upfront more education, make sure people are familiar with the Java language and the Java technology, then that will be a preventive action from making many of the Fortran-like mistakes. And sometimes they say, oh, I have in the program that I have open parentheses without closed parentheses. That's very often, okay? And we did that all the time, and you do that with the programs, with documents, with all kinds of things, open quotes without closed quotes, and you can think of that with ideas. You have some ideas, you expose the ideas without conclusion. You can think of that one as not closing something out, but that's on the semantic level, not at the syntax level, okay? And if you have some open ideas without conclusions, the people will be sometimes perplexed, but sometimes you purposely want to do that, okay? So that in mysteries and things that you want to have something left for people to imagine. You don't want to have the closed parentheses there, okay? And but in programs, we must have. We shouldn't leave anything to speculations, okay? And so in that case, say, for example, that if I have a tool can automatically balance the open parentheses with the closed parentheses, then I won't have this unbalanced things, the problem. If I have a tool, typically it's kind of as an extension to some compiler and the development environment. I'm working in the Java environment, okay? And then I have some tool for me to build Java programs. And make sure as I write the code, it automatically checks that this is the correct Java syntax. Okay, so if that's the case, then I don't have to worry about the syntactical errors, right? The syntactical problems, okay? So I won't have those kind of fault in my system, okay? So you may be able to build in some of the defense upfront for the prevention, okay? So in the first case, we said, okay, you can educate the people so they know Java technology, Java language and technology, instead of just knowing Fortran and a little bit of Java. Okay, and in the second case, we say, okay, you can have some tools and technology that can help you automatically correct some of things, preventing wrong things getting into your code. Okay, so those are the upfront defense. So you can look at some of the errors get removed. Some of the errors get removed because it's blocked. It cannot get through. That kind of illegal action will not be allowed by using this technology. Okay, and sometimes that through education, through some better processes, through some other things. Okay, so as error source removal. And another thing, possibility we mentioned about in the health analogy, we said, okay, with health, we use immunization a lot. Okay, we use immunization. What we have in immunization, the basic principle is that you introduce that problem to the body, and then try to help the body build up the immune response so they can deal with it, either kill it or tolerate it, or not make it into a big problem. Okay, so with smallpox, with all kinds of things, we do use that kind of mechanism to do it. In software quality assurance, there are some ways of doing that as well. Okay, so one of the things that is that in software, among the software technologies, sometimes people do so-called defect injection. Okay, so in defect injection, is they're doing the defect injection test, the mutation test, and those kind of things. Is that they in that case, it's the sad part is that our software, we don't have the very strong immune system like what we do evolved over millions of years. Okay, so we have less capability to tolerate fault in the system. In our human systems, we have lots of faults and we deal with it. We tolerate it so it will not kill us. Okay, but in software, we don't have that capability yet. So what we do is that kind of artificially add some of that capability by one of the ways that later on we will talk about this a little bit is that you try to inject some fault into your system, okay, and then you look at this system after you inject the fault, run this system against your test or test suite, many of the different test cases, and then look, can you catch this fault that you just injected? If you can, that's good. You know that by running through this kind of test, this kind of problem will be all caught. Okay. If you cannot, then try to improve your test cases, improve your test suite. So that's kind of like building your immune system. So your enhanced test suite will be able to kill this problem. People call this kill this problem or kill the mutation or things like that. And that's some of the things that people consider also. Yes?
So is that the way you test fault tolerance in the system?
Not exactly. I haven't introduced the fault tolerance here yet. It's in this case, we are still trying to fix the problem, not tolerate the problem. Okay. So in most of the defect injection testing, we try to have this kind of mechanism, add the mechanism as if we added an immune system, so that now I enhance, strengthens my test suite, so it has the stronger capability of catching problems and fix the problem. But the other way of doing that is that you can tolerate this problem. Okay, so you mentioned about that. That's this last defense line here we look at it, is that, well, we mentioned about if you give me an answer to 5, I don't know if that's correct or incorrect. I ask someone else, okay, and someone else said the answer should be 4. 2 plus 2 should be 4 instead of 5. Okay, in that case, I cross-check and then I can detect some problem. Okay, and if I cross-check, I can detect some problem. I go back, can fix the problem. But suppose it's the wrong time. I don't have time to go back and fix the problem. Then what do I do? Then maybe I can have some kind of redundancy, duplication built in. Instead of asking one program to do this calculation, if I really need to trust this thing, really rely on this thing for lots of important things, I can say, okay, I ask 3 programs to do the same calculation and compare the result and take a vote. Okay, when I take a vote, say 2 out of 3 said the answer is 2, answer is 4. When I enter 2 plus 2, 1 said it's 5. Then I outvote that 5 out. In that case, I didn't correct that fault. I didn't remove that fault. The fault is still in the system, but my system will perform correctly. Right? My system will give me an answer of 4 instead of 5. Okay, so there's no failure. There's a fault, but no failure. Okay, fault but no failure. That kind of mechanism that we build into the system, into the software, that's called the fault tolerance. Okay, so we tolerate the fault by some kind of redundancy, cross-checking, and redundancy. Okay, and of course, fault tolerance is not just limited to software. It's a really we got the idea from many different places, from from nature, from all kinds of other design and things. Okay, so think of us that we have 2 of many of the different things. Okay, we have 2 eyes. Okay, and so that had some fault tolerance, innate fault tolerance built in. Okay, and when you look at the airplanes, they have multiple engines that had the fault tolerance. Okay, so sometimes one engine had a malfunction, and you can still have the airplane functioning. I remember one time they had something that had one engine not working, and they still flew over the continent. Something like they had a problem where they flew from somewhere in Asia to Europe or to North America or something. Okay, so you have those fault tolerance. And in software, we will be looking at some of the ideas for fault tolerance also. Okay, so those are just some of the ideas. And then there is also the last line of defense here is that, well, if you do have a failure, sometimes that I want to do something about the failure characteristics so it will not be so bad. Okay, and so in that case is that I may still have a failure, but it's a failure of less extent. Okay, so one typical example people give here in this kind of situation is that you think of some safety critical systems. Okay, think of a lot of equipment in operation. Okay, when power fails, okay, when you have a power outage, okay, then you should make sure that your system will be in a safe state, not cause accident. Okay, so if you think of that, there are a lot of design issues that people deal with, grapple with. Okay, so I was an electrical engineering major in my undergraduate studies. So I remember that example really vividly from one of my professors in those early days, talking about the control systems and look at the things that active versus passive control and things. Okay, so when the power is on, you overcome some resistance to make the system operational. When power is off, your system should stay in a situation that is inoperable but not causing harm. Okay, so when power is off, you should not let the system go have a free fall, free things. So like in the elevator, when the power is off, whenever power is off, it should be locked in its current position. Okay, so essentially, when you design the system, is that when power is on, you unlock the mechanism and move the elevator around. Whenever the power is off, the stable state to return to is that lock in the position. Okay, so you can design this kind of a mechanism into the software, and then you can do all kinds of things in software that look at you have software, hardware interlocks and things, and then, for example, we had that fault tolerance things. We say, okay, we have a fault tolerance. 2 out of 3 voted yes. We say, okay. But what if I don't have that level of redundancy? I have just the level of redundancy of 2 things. When they don't agree, what do? Well, I don't do things based on this computation result. I stop this. It's not going to cause as much harm as if I go ahead using this result to do other things. Think of this. The computation result is the medical dosage. I have 2 procedures. They, one said that you should use this 5 milligrams of things for this. Another one said that you should use 500 milligrams for this. Okay, so you don't know. You don't know, then say, don't give the medicine. Okay, do something else. Stop this. So the system will stop. In this case, it's a reliability problem, right? It stopped. It didn't give you a correct answer. But it's not going to cause further damage. Okay, and then you have to wait and then maybe get an experienced pharmacist to calculate this for you instead of rely on your 2 programs. Okay, and then the pharmacist will be overriding the things and say, oh, okay, instead of 5, it's not 5, it's not 500, maybe it's 0.5. Okay, and so in the case that you give 500, maybe you'll kill someone. Okay, and give 5 will probably make someone sick. Okay, because it's supposed to be 0.5, for example. Okay, so you have to do something about this result, and then look at this. In this case, is that your system failed, but your system failed with a less damaging failure than a more damaging failure. So when you have this interlock, whenever there's some problem, inconsistency, you stop the system. You don't let it go further. Okay. So in some sense, you are doing something on the failure side. It's still a failure, but it's a failure of less damaging characteristics than otherwise you let it go and use it to make other decisions. Okay. So that is a part of quality assurance also, that we try to guard against this more catastrophic failures. Okay, to try to lessen it, weaken it, okay, and make it less of a problem. Okay, so in software quality assurance, and we call this one some kind of their reduction of the problem characteristics and severity, and sometimes this is particularly for the safety critical systems, so that we have lots of so-called safety assurance techniques that concentrate on working on looking at the failures with less damaging impact than otherwise. Okay, so that's a kind of a high level. And then what we will be doing after the break is that for each of these techniques, each of these strategies will go into a little bit more and looking at some of the basic ideas behind those techniques, and then you can start to think and consider whether some of those things might be appropriate for you to use in your course project. Okay, so let's take our second break, and when we come back, we'll go to a little bit more detail. So at this right now is we are kind of at the level of detail for chapter 3, but now we will go. After break, we'll go into a little bit more details than in chapter 3, and looking at a little bit more specific mechanisms of doing this and that. Okay, so let's take a break for now.
Well, I know what the guardrail is, but like, how do you, can you walk there from here, or do you catch a bus? Oh, that's slow, especially at night. Where's the bus? Huh? This is the only course I'm taking this semester, because I work full time. It's a financial financial, so like, I want to call, they're the people who sponsor the actual. It was an option for the elective. So most of the classes were
have already seen
This line right here, like.
It is not
Yeah, so not right here. So like this little line.
card based.
That's what that is.
Only a few.
That whole thing is just like I'm glad I'm not. Sounds like
As soon as
Oh, this one.
so you can highlight. No, we're gonna have to recapture. I think so too, because I think all of them.
Some people sense that
Yes.
you
You gotta get a percentage.
these are really want to expect the
Cause I was so last year.
more than that's the reason why they do it what's called the front line.
I think I waited for last year. Cause I was like, I think I'm home to come from.
Yeah, we'll be there.
You know.
We lost the problem like 15 months. So it's
What?
going
Our Spanish stuff?
don't be hesitant to find them.
Our Spanish? Let me see.
Usually only one dimension.
I can see. He has design too, I can say that. Far. Huh?
Okay, let's go back to our class, and we try to try to wrap up as much as we can on this part of the different QA activities and the main ideas behind those things. And so we will definitely finish that part by next week, and we can talk more about your project. Okay, so let me switch over back to the computer. So we looked at this picture and they said, okay, the basic strategy is that there are faults in the middle. We try to remove them. That's one big category of quality assurance strategies. Okay, and then we can try to do something on the error side, okay, error and error source side. So we do the kind of defect prevention. Okay, and then we can also do something about defect that's still in the system. We try to tolerate it, try to deal with it, try to because sometimes we tolerate it, sometimes that it still causes failure, but not as severe. We call this whole thing the defect containment. Contain it in a sense that sometimes if it will not cause failure, that's better. If it's a cause failure, if there's some mechanism we have that can we can alter the failure characteristics, make it less damaging a failure that will be more desirable as well. Okay, so consequently, what we said here is that this is our classification scheme, that we have the defect prevention, defect removal, and the defect containment. Okay, and so in terms of this, then we have the prevention side, have the preventing the fault injection. Okay, so we can either block the error. Okay, the direct block the error or remove the source. Okay, in the removal side, we mainly focus on inspection and testing. Okay, we said that some replacement strategy might be a good thing to consider as well. Okay, so we are not saying this. What we have here is exhaustive, but they are the main things that we will be covering. Okay, failure prevention and containment. So we look at the overall defect containment is that sometimes we can prevent the failure from occurring, even with fault. That's the fault tolerance. And sometimes if we cannot prevent the failure from occurring, we try to change the characteristics of the failure to make it less damaging. Okay, and so in some sense is that we are dealing with reducing a major failure into a minor failure, or catastrophic failure into a major failure, something like that. So typically we're dealing with so-called safety critical systems, and in safety critical systems, a failure with a severe catastrophic consequence is called an accident. So we try to prevent the accident from occurring, even if you have a failure. Okay, so for example, in that elevator example I used before, that free fall of elevator, and that maybe causes people to die and things like that. It's an accident. Okay, but the elevator not working is a failure. It's not an accident. Okay, so elevator not working is not an accident. Okay, and you can call it an incident, but it's not an accident. Okay, so those are the major things. So what I'm going to do next is that actually I do have a lot of slides for this corresponding chapters from 13 through 13, 14, 15, 16, 30 through 16. 17 is a comparison of all the things. I do have a lot of slides, but I'm not going to use those slides, but I'm going to kind of talk a little bit more about those different strategies, and we will. But it's probably a little bit more than what we have in those slides here. Those slides here are basically the basic ideas that we discussed so far. Okay, so for example, with the defect prevention, we try to do one of the two things. Either you directly block the errors, because the errors are the missing or incorrect actions that leads to the injection of fault into the system. So what you have there is that, well, if something is missing, action is missing, if you can automatically supply it, it will no longer be missing. Okay, so for example, one of the things that we talked about is some kind of a tool to balance the open parentheses with the closed parentheses. So in your development toolkit, okay, in your programming tool, whenever you have an open bracket, there will be automatically a closed bracket inserted. Okay, so in that case, it's guaranteed to be balanced. Okay, and then whenever you have a closed bracket, it will find this open bracket corresponding one. If you cannot find it, it will close it also. So in this case, is that because of this error is a missing or incorrect action, this missing action will be automatically provided. So you won't have that missing action anymore. Okay. Of course, then you say, okay, can I do this for every kind of error? Probably not. But for some small kind of percentage of the errors, okay, something that we may have a tool to do this. Okay. This will be working on some of the things that you can model with a tool, with the analyzer. Okay, so most likely something like in our example, syntactical problems, then you can do it. Okay, but if it's doing with the meaning, with the ideas, probably it's hard to automatically correct those things. Okay, we mentioned about the ideas so that you have some open ideas and without closure. Well, it will be much harder to provide automatic closure to your open ideas. Okay, so we probably can stay in the low level and do some of those things. Okay, and of course, then you say missing or incorrect actions. So some say you say, what about the extra actions? Oh, extra things you can think of that's some incorrect. So when it's extra, you can delete it. Okay. When it's incorrect, you can correct it. Okay. So for example, that in different programming languages, there are some of the things that's quite close, but have completely different meanings. Okay. Like for example, that simple example of single equal and double equal. In many different languages, they have completely different meanings. Okay, single equal. Unfortunately, from the early days, we have been using this for assignment. Okay, x equal to a plus b plus c plus something. We are not talking about the equation. X equal to this thing, and we solve the equation. That's not the mathematical equation in most programming languages. It's actually x got the value of a plus b plus c times something. It's whatever in the right of the equal sign got calculated, and the value got carried, assigned to something on the left. Okay, so it's really an assignment. It's not a mathematical equal. So there is this semantic confusion here, because we normally in mathematics equal means equal. Equal doesn't mean assign. Okay, and so sometimes people mistaken this one, equal and assign, and so the comparison operators. So for example, that single equal and double equal have different meanings, and then when you do the single equal, then maybe the system can query you whether you are using single equal or double equal here, and things like that. Okay, and actually this is a place where you're likely to make those kind of mistakes. Is in testing, you can do some so-called mutation testing, and so look at your test cases. Can you distinguish between single equal and double equal or not? Can you distinguish between equal and not equal or not? Okay. Can you distinguish greater than from greater than or equal to or not? Okay. So oftentimes we have those kind of operations in our programs that need those kind of things, and so sometimes this, if you have some facility can help you with that, that can help you with preventing some similar kind of problems being injected into the system. And sometimes if it's in the system, you can use the so-called mutation testing or similar kind of ideas to distinguish between those different alternatives and try to find out whether you had the correct choice or not in the first place. Okay, so that's the error blocking general idea, and then there is also the so-called error source removal. idea, is that you look at the root cause of this. You did this because you were confusing the meaning of equal sign with whether it's a comparison, it's a mathematical equal, or is that the assignment, okay? And so if there this confusion there, then you should try to clear up that confusion before you can proceed further, okay? So that is the place that you can do some education, you can do some training, and sometimes that people are, okay, I also mentioned about the interface problem. That module A is calling module B with the incompatible parameters, okay? And in that case, you say, okay, what is the problem? Well, the problem is that they are incompatible parameters. And then what's the solution for that? Is maybe you do have a standard dictionary, standard description about when you have interfaces, what are the expectations of the interfaces, okay? So you have interface guidelines, design guidelines, you have design guidelines and you have standards that you can follow, rules you can enforce, okay? So you have rules that you can enforce in this case, and that you come up with the rules and then enforce those rules. That will be a solution to that, okay? And when you have the rules, and typically people do have all kinds of rules. People have all kinds of standards. They say, oh, okay, well, we are using the ANSI definition of this, and we use this and use that, and we use the rational development process, okay? And so the thing that some development process that is supported by the rational tool suite, okay, and things like that, okay? Well, are you following those things? Okay, and do you have a kind of process of handling this kind of things, resolve these things? Okay, so lots of those things can be boiled down to some kind of a systematic way of dealing with things. Okay, if you have want to have a systematic way of dealing with things, typically you will have to follow some process, some kind of a standard process to resolve those things. Okay, and have those processes defined, followed, and monitored, improved, optimized. Okay, so oftentimes that people are looking at the defect prevention, people look at the so-called process improvement. Okay, so looking at their some of the process work, and they're looking at how do you do this. Okay, later on we do have a chapter in our book. Okay, we will spend some time on that. It's looking at the defect prevention and the process improvement. So the process part, we will be looking at different mechanisms for doing that. One of the such process-focused work is the CMMI. Okay, so the SEI from Software Engineering Institute, they have the capability maturity model, and a lot of things they had the quality focus in there. Okay, but their main goal is to do the defect prevention. Okay, so they are not looking at individually looking at the defect removal and those things, and they look at your testing process, your development process, look at how those things are defined and how different things are addressed, but you'll look at the overall process of maturity. But then there are some of the process-related work that kind of focus a little bit more on quality directly, because CMM is focusing on the whole project success. So the cost control is an important part of schedule. Quality is only one part of it, success story. But there are some framework looking at the process things is focused more on the quality. Like the QIP, we will spend some time on later on. quality improvement paradigm. Okay, QIP was initially proposed by Vic Basili also, and he was working at the time with NASA and with some other industry, doing research at the University of Maryland, and came up with this thing that so-called quality improvement paradigm. So essentially, whatever you do, you have this kind of continuous improvement as the basic framework. With continuous improvement, what you need to do is that you first you have to know where you stand, okay? Because if you don't know where you stand, where do you improve? Improve over what? Okay, so you first have to understand the current situation. Okay, establish a so-called baseline. Okay, so you look at the so-called baselining. Okay, and then if you want to do some improvement, then you look like if I do this improvement, if I make this change, I want to say before I really commit it in the production, in the overall deployment, I try to see if I can do this in a small scale, pilot it out, and look at what kind of impact it's going to have. Okay, and then if the impact is what I want, then I can go back and deploy it. Okay, so that's the basically with the baseline, small step trial and error to improve on the things. Okay, and actually I think that there is something that's kind of interesting about this is this kind of a framework in the software engineering community and in industry. It was the first kind of got wide adoption in Japan. Okay, they were kind of more tuned into this kind of continuous improvement philosophy. Okay, they are so they did this. Okay, and together with this, of course, you want to establish your baseline. When you establish your baseline, and then you want to look at also the next step, you want to look at what's the impact of your change, and then you can adopt it. But both establishing the baseline and getting the impact assessment, you need some kind of quantitative measurement. Okay, you need to quantify those things. You cannot just say wishy-washy, this is this, this is that, but you try to quantify that. You need some measurement framework. Okay, so your measurement framework to support this one is through the so-called GQM, goals, quality, goals, questions, metrics. We mentioned about that in the quality frameworks before. Okay, so that can help you with the quality improvement initiative by looking at what is the area you want to do, what's your goal, and then refine your goal into questions, and then you can get some metrics that can help you quantify those things. Okay, and then for the operational support, because you want to do the quality improvement, then the quality improvement, the operational support, it's hard to ask the product development organizations to improve upon themselves always. Okay, they do self-assessment, they do all those things. Okay, so as the implementation of support, Vic Basili suggested that you use the so-called experience factory. Okay, so you have the software quality groups that serve as the experience factory. Okay, experience organization, collect those experience and then package them. Okay, so that generalize them into some kind of experience base. When you need to support a specific project initiatives, you can package them and so support those things. So a lot of organizations, they have the so-called SEPG, software engineering process group, software quality group, software engineering process group. They essentially work in the role of trying to be a experience factory for the overall product organizations. Okay, So those are some of the related work in that area, and we will be talking a little bit more about those things later on after the midterm exam. A little bit, kind of 3/4 of the way into the semester, we'll talk about some of those things. Okay, but when you consider your project, you consider whether some defect prevention is can be a part of your project as well. It's probably going to be a little bit harder to do in your project because your project will involve testing, and most of the things are probably already designed, committed already. So defect prevention is probably a little bit too late, but at least on the long term, you can think of some of this defect prevention process improvement. Okay. So that's this one. I'll skip this one for now and do the inspection first. Okay. With the inspection, we mentioned about the general idea of inspection. Actually, let's do the testing first because we talked about testing much more. Okay. So testing, we will talk much more about testing later on. Okay. But the main idea of testing is that, well, you are looking at testing as a way to remove defect in the software process. Okay. And then what you do is that you observe failures, reproduce those failures, try to do some analysis, localization to locate the fault that caused the failures, remove that. Okay. So when you do this, you will be testing something that's already implemented. Okay. So when you characterize the testing, you will have to look at well, what kind of things are you testing? Okay, are you testing what kind of product, implementing in what kind of language, what kind of technology you used for this implementation? When you do the testing, what scale? Are you testing the whole system? You're testing a small piece of the system, or what? Okay, and who is doing the testing? Are you doing the testing yourself as a developer? Or you have professional testers, or you outsource. Okay, and actually nowadays that testing become a kind of a little bit more common kind of things for people to consider outsourcing. Okay, some people, some organizations are providing testing services, and another thing is that oftentimes that if you have a testing and development. Although by different people, if they are from the same organization, they may have some common interest. Okay? And sometimes that you can say they have conflict of interest. Okay? Because, say for example, if you want to sell something to the customers, testing not only removes the defect, but also demonstrates its good quality. Right? And then you say, I passed all those test cases. Now I can pass all those test cases without problem. So that is a kind of a badge of quality, a stamp of quality. Okay, and if you are trying to sell this product, then of course that you say you want to, it's in your interest to say this one is of good quality rather than it's a bad quality. Okay, so if you have a market, you have a lot of competitors. Then the market will decide that is a good quality or bad quality. But in some other situations, you don't have a lot of competitors, you don't have the market to decide that. This is a particular situation with government contractors. Government need to have thing, or they need to have something that provides software and hardware and things for the space shuttle program. Well, you don't have 15 developers providing different things for different space shuttle programs. You only have one space shuttle program. Okay, you probably have only one provider of this. Okay, you have something for the NASA for the satellite and the things. Okay, and in that case, that you want your testing report to be as objective as possible. So in that case, you want to have some kind of third party, IV and V, independent verification and validation. Okay, so you may have those kind of things. So your testing is performed by a separate organization. This is particularly useful for the government contractors in situations. Okay, and so when you do the testing, you do from the external point of view, from the internal point of view, black box versus white box we talked about. Okay, so it's you look at the verification view versus the validation view. Okay, the black box and the usage is mostly look at the validation. This one is really doing this thing I wanted to do, and also had some verification aspect. Is doing the overall things seems to be correctly. But when you look at the white box internal testing, it's mostly looking at the verification. Verification, it conforms to this design constraints. My code conforms to my design intentions. Okay, my low-level design conforms with the high-level design. It is in agreement with the high-level design. Okay, and my high-level design is satisfying the requirement. It's in agreement with the requirement. Okay, so you have lots of those things that you get. And so testing serves the purpose of both verification and validation. Okay, and it will help us from the defect point of view, help us try to locate, discover, observe the failures, locate the fault, and so as a result of testing, we can remove the fault. So the defect removal. Okay. Of course, we later on we will look at the testing. Testing can also be used for another purpose, is the quality demonstration. Instead of just saying, I can detect this defect, remove it, I can demonstrate it is does not have this kind of problems. Can demonstrate of the demonstration of quality. Okay, and of course when you do the testing, one of the important thing about testing is that about testing or about many other things is that when do you stop testing? Well, with development, you typically have a very kind of more concrete criteria. When do you stop implementation activity? When I have all the functions implemented. Testing, you say, when I have all the functions tested. What do you mean by all the functions tested? You cannot test all the combinations, all the possible input. No way.
You can have partition.
Yeah, so you can do the partition, you can do this, and you can do that. Okay, and we mentioned about the partition, and we mentioned about the boundaries, about the extreme cases, and so you have to have some kind of criteria to stop testing. I test all the partitions, I test all the important cases, I test all the important usage. Okay, so you have some kind of criteria. The best kind of criteria, because if you want to be successful in the market, customers care about they don't have problems. They don't care as much as how many internal problems you have. As long as you don't have problems for my applications here, I'm fine. Okay, so from the customer perspective, is that is a reliability. The quality in here is the reliability is defined to be the probability of failure-free operations for a given time. Okay, so for a given time, you'll have higher probability of no failure. You have higher reliability. For a given time, you have a lower probability of no failure, then you have low probability. So for example, for a given 1 year of operation, I say I only have 0.001 probability of failure. So I have 9.999 probability of failure-free operation for a year. That's good. You say, okay, for a given year, I have a probability of failure very, very high. Okay, and I only have something like a 0.1 probability of no failure. Okay, then that's pretty bad. Okay, and then sometimes you can measure it in or turn the probability around and say, what's on the average length of time between the failures, from one failure to another failure. Okay, so for one thing, I can have the average mean time to failure of the average amount of time to failure is something like 10,000 hours of operation. You have another product that fails every hour. Then, of course, that one with 10,000 hours of operation failure interval is much better. Okay, so you can measure those kind of things. And then when you measure those things, you have to say, okay, this on the average over what? What kind of usage? Because if you use the system differently, it's going to fail differently. Okay, for example, that you have a database will be used by many different people, different organizations. If you have a database, people just use the database to manage their own banking account and some other, their budgeting and things. Probably you don't need much capacity, too much capacity. But again, it's hard to say because people now accumulate so much things in their life, okay? And so it's probably going to be different than Bank of America. They have a database, they manage all the customer account and the things, okay? That's really different, okay? So Bank of America using a database will be quite different from me as an individual using the database, okay? So then you can say, okay, your reliability is for Bank of America kind of usage or for individual user kind of usage, okay? So you have to do this. And then in a sense is that if you target big businesses, then you really have to have your testing resembles this usage environment of Bank of America and other the large businesses. Okay, if you target individual users, then you probably don't need something as big, but you target those individual users. Okay, yes.
It also depends if you are using a critical system, for example, a nuclear thing, or
Yeah. The criticality of the applications as well. Okay. So you look at those things, then with reliability is that you have to kind of look at to improve my reliability, I need to know how my system is used. Okay, and then when I know how my system is used, I can test accordingly. That is usage-based testing. Okay, so I can test my system accordingly, and when the system I test reach the reliability level that is the expectation of my customers, then I can release my product. For example, in the telecommunication industry, they expect that your major telecom switch products, the downtime of a whole year of operation, no more than a couple of hours. Okay, so that's the expected level of reliability. Okay, and if your product cannot meet that, then you simply will not be able to be competitive in that market. Okay, and you can reach that level of reliability. Say, I still want to do more testing. Then probably you don't want to, because you do more testing, you will spend more money, and your product will be more expensive than another suppliers, which meet the expectation of the customer. So sometimes is that we try to do a good job, but we want to do good enough job for the money. Okay, we don't want to indiscriminately be the perfectionist. Okay, and then you will carry on forever. Okay, and then your product will never be ready. Okay, so we cannot be unrealistic, and we cannot be really just strive for perfection. So those are the different things, and based on those three big bullet points, we have different ways of looking at what kind of testing are you going to perform. Here, what are you checking? Are you doing the black box versus the white box? Are you looking at it from the external customer point of view, or looking at the internal structural development point of view? Okay, and are you checking the functions, or are you checking the elements and the structures of your system? So you can do black box, you can do white box. Okay, look at the criteria. Are you doing the coverage-based testing? I cover all the cases. If I cannot cover all the cases, I cover all the partitions. I cover all the boundary conditions, or I'm doing the usage-based testing. I do things based on the usage. If my customers use this kind of scenarios more, I test these scenarios more. If my customers use these scenarios, big setup more, I do it. And if my customer uses this other scenarios less, I test less. So that's usage-based testing. Okay, and then we can also distinguish testing by what kind of product you are testing. Okay, you are doing the software testing, you are doing the testing of the Java programs, you're doing the testing of the C programs, C++ programs, you're testing the web applications that's implemented by various other things, okay, including some some script and some HTML things, okay. Are you testing what? Okay, so you can test all kinds of things based on the kind of the product implementation, product, what kind of function area, telecommunication product, testing a database product, testing an application product, testing a game product, testing a website, testing an embedded system, testing what? Those are the things. I will test the whole system, testing the subsystem, test a small unit. Okay, so you have those different test phases. Who's doing the testing? Okay, and you can look at all those things. But very importantly, it's not in this page. Is well, if you want to do a good job, you have to do somewhat more formalized and systematic testing. If you want to do systematic testing, there must be some kind of theory and model for, kind of you can rely on to help you do a good job. Okay, so one of such a kind of theory of model we mentioned about the coverage and the usage is that, well, you have to define some kind of coverage, some kind of usage. How do you define this coverage? How do you define this usage? We mentioned about partitions. Okay, so you cannot test everything, so you divide the whole overall input space into the different partitions. So effectively, you say, okay, if this is a, switch over to here. So say this is my input space, okay? If this is my input space, there are many points in this space. Basically, if you think of all the numbers in this input space, say this is a two-dimensional space that you have x and y, there are infinite number of combinations here, okay? X and y, yeah, you have an infinite number of combinations here. And they say, okay, can I do the infinite, even if you consider the precision and the number system in the computer, you still have an astronomical number of input combinations, x, y pairs. So each point can be a testing point, and there are infinite number of points, or just such a big number of points that there's no way you can test them all. If you cannot test them all, you say, I can partition them. There's some things, this is the A, and something, this is the B, and something here we have a C, and then we have a D here, and we have a E here, and then we have a F here, okay? Something like that. Well, in some case, I can divide this into things that say, okay, I'm testing something about people filling out something about their things based on their geography, and then I can say, okay, people from Texas are doing this, people from Oklahoma are doing something, people from New York, California, they're doing something differently, and then I can test based on the geographical locations and think, I can make sure this works for Texans, Californians, for New Yorkers, and for everyone. And so I can maybe have a representative sample. In this case, the 50 states. I can have one from each state and one form from each state, and I can make sure that it works. Okay, so that then in this case, then I'll have 1 point here, 1 point here, 1 point here, 1 point from each that I can do this test. Okay, so this is the partition test. Okay, so I can do the partition and doing the partition coverage. And how do I do the partition? I have to have some kind of structure, some kind of theory about how do you form a partition and doing those things. Okay, so that's a partition test. Okay, and then based on the partition test, I can extend this. I say I'm using this one more often. Okay, 0.8 probability I'll be using this. 0.001 probability I'll be using this. 0.01 here, 0.1 here, and then the rest you can distribute them. Okay, so in this case is that say A is much more important. Okay, think of the elections. California, Texas, New York, Florida, they are more important than Wyoming, Idaho, and those other states, right? In the presidential election, okay, because you have more votes. So people probably, if you think the presidential campaigns, then they won't spend the same amount of money in Wyoming as in Texas or California or New York or Florida, right? So you will spend more money in those big states. Okay, so in a sense, is that they are following the usage-based testing strategy. Doing things. Okay, so I will be spending more of my resource here. In this case, this is so important. It represents 80% of my usage. So I will test it much more thoroughly, and then maybe I have lower level models for this, and so I can test it more thoroughly. Here, I just maybe test one of each, and maybe here I test a couple, and here I test two, here I test one. And in some cases, it's so insignificant that I gave up. I don't test it. I don't test this part. Okay. So in that case, it's an extension of the partition based testing, but we do the usage-based testing based on this underlying theory about partitions. Okay, underlying model and the theory about partitions. Okay, and another case I say, okay, with the same kind of model, same kind of theory, I say, most likely when I'm on the borderline case, I'm most likely make a mistake. This is with numerical processing, we do that all the time. Okay, so for example, 0 is an important case. You divide by 0, okay, positive, negative, okay, but 0, not okay. Okay, and so that's a borderline case. And then you have something belongs to this, okay, belong to this class or belong to that class. That is important thing. So sometimes they say, okay, I want to test around this boundary point, okay, instead of just sample the interior point. I want to do this boundary point. Okay. So in that case, what I'm doing here is that I'm doing the so-called boundary testing as an extension of partitions. Okay. So I'm doing the extension to the partitions, doing the boundary testing. So using this model, the basic partition model, I can support several different testing techniques that can be used for black box testing, white box testing, coverage-based testing, usage-based testing. Okay. And of course, we have some other models that we will talk about later on, that more complex models than this. One such model is the finite state machine. Okay. We can use the finite state machines, okay, to look at their connections, their operations of a different part of the program, and how they are connected, how they operate, how they depend on each other. Okay, so with that, we can have the basic finite state machine try to cover the states, the transitions. We can do the overall flow from the beginning to the end, how many paths we have. So we do the pass testing. Okay, and we can look at the data involved in that of our operation. Which data depends on what? We can look at the data dependency and do the testing. Okay, so we had here, we had those questions, but we didn't say what models are you using. Okay, what models are you using will have a big impact on what kind of specific testing techniques we will be using. So we'll be talking much more about that, and we haven't talked about the inspection, fault tolerance, and also since I will try to finish up that, and then we doing a little bit more testing, and then I will talk about the project, so you can think about what kind of things you want to do with your project. Okay, and so that's it for today, and I'll try to see. I don't think you'll have enough things to finish the first homework assignment. I want you to do to cover the whole first part of our book, and so I'll probably post something in a few days, and you can start, but you probably won't be able to finish it. But it won't be due until after next class. Okay, so yeah, that's it for today. Good night, and see you next week.
Also, Blackboard will be consolidated this week, yes? For like, for this.
Yeah, I think so. The Blackboard, yeah.
Okay.
Okay, yeah. Okay, see you.